Right, welcome back everyone. I hope you had a nice break. And yeah, we are like in the last week of this semester, like in terms of lectures at least. A few announcements, and I sent out an email as well. I don't know if you have if you had a chance to look at it, but I can go over that quickly. So first of all, the gradable for the final project report is open, and it's due. It's not due until next week, Friday night. So you have time, even if you're presenting like on Tuesday, that's fine. You still can tweak your report, and you can submit it like by next Friday. Okay. The other thing that I wanted to point out is if you go to the discussion forum, I have this post here. If you go to the link, I just created this Excel. You can just go ahead and edit it. So for example, like there are 2 days when we have presentations. So either it could be on Tuesday, December 7th, or Friday, December 10th. And again, you can tweak your project report and submit the final version on Friday still if you're presenting on Tuesday. So what I want you to do is just like go ahead and add a row for your team. So for example, here you should add the names of all your team members and the topic of your presentation and like which day you would like to present. And this is just to take your like preferences, and I would try to adjust as much as I can based on your preferences. I would line up the presentations. However, if like everybody said that they want to present on Friday, that's going to be difficult. So we'll have to like split the team like into two. So yeah, I mean, I would definitely like to take your preferences into account when deciding when like the teams can present, but like we just have 2 days, so we have to figure out according to that. If you have questions around that, feel free to write in the discussion forum, and whenever like I get a chance to look at it, I'll come back and answer that. And we still have time, like uh, we have a week until the presentation start. And let's say I assigned you some day and then there was like something unavoidable and you cannot present on that day, just like email me and I'll try to like make some arrangement so that like I can move it or something like that. All right. Any questions about presentations, about the final project in general? You know that you have to submit a final project report. And as I said, it's not due until Friday of next week. All right, so we are in the last week of lecture. This is lecture 24, and we just have one more lecture left. And today we are talking about, in general, the rise of deep learning and how we came about in this era when almost everything that we see around us has one way or the other some application of machine learning and AI. So we'll talk a little bit about the history of AI and how we reached at this point where we are. So that's the first thing. And then we have talked a little bit about some limitations of deep learning. For example, we talked about there is this lack of interpretability, there is lack of understanding of like how we are getting the results. There's like these deep learning models that act as black boxes. And the other thing that we haven't looked at is there is some uncertainty in neural networks, obviously, but we are not capturing it. So can we do that? By capturing, I mean, you know, linear models, right? And then when you like get an estimate for a parameter in the linear model, you can come up with a confidence interval for that particular variable, and you can say that well, like with 95% confidence level, this variable lies within this range. We can do that. We have statistical tests available, but we are not doing that for deep learning point estimates or even probability estimates. And that's important because that's how the trust can be built in these models. Right, so we'll talk a little bit about that. This is a very like recent research area, I would say, uncertainty in neural networks, and there are like some models that have come under like a lot of focus these days, and we'll discuss them as well. So just like some idea of how this uncertainty can be modeled in neural networks. Okay, so let's begin with the first one, which is rise of deep learning. And this graph here sort of, let me just make it a little smaller, this graph captures like over a period of, I would say 70 years, almost 70 years, how deep learning or specifically AI has progressed in terms of its usage, its applications, research, everything, right? So we can say like with confidence that the term artificial intelligence was coined during the 1950s, so specifically 1956 in Dartmouth conference. And that's when like a group of scientists, so this conference was about some workshop that was held about um, intelligent machines. And then like a group of scientists and mathematicians came together to sort of do a brainstorming session about like how machines can learn and how can we build more intelligent machines. And there this term was coined that's known as artificial intelligence. So that's when it all started in 1956. And of course, like there were a couple of known good research outcomes that came about in the 1950s. But then we saw in the mid 60s, like this AI winter. And so these are like these dips in the curve are known as AI winters. That means there was a lack of like the usage of these models as much. There wasn't any application. And like in this first winter, it was due to limited processing power that they had that time. Because now we know that these are like data hungry models and they need a lot of data, but like along with data processing comes the processing part, right? And then they didn't have enough resources to do that. Limited database storage capacity, limited network ability. So that's why we saw this dip, and there wasn't like as much enthusiasm around AI during this time. But then there were like Edward Friedenbaum is known as a very like he's a well-known scientist in the AI community, and he came up with this expert system idea around like the mid 70s and early 80s. That's when we saw another like peak in the AI research in the not just the research but also application part. So that was around 1975 to 1982, and then again as the research progressed in these areas, as applications progress, you now know that like if we don't have the present computational ability, this cannot go any further, right? We'll just have like some toy models built, but that's about it. Like your model is as good as your data is, and as much as data like you can feed into these networks. So that's why we saw another dip, which is known as the AI Winter 2. And this was not just because of the lack of computational power, it was also because there were some like disappointing results that people were getting. So the models were not as sophisticated as they are right now, and like failure to achieve scale. And then the other thing is the amount of hardware and the level of hardware that's required to process these and like extract the full capability of these models. You need specific hardware, right? And we know that it is becoming so much easier right now. And as a result, we are seeing this like steep rise in the usage of machine learning and AI, right? So we are luckily in this area where we are seeing this extreme rise in ML and AI systems. And then deep learning came about sometime after 2010. I wouldn't say it came in that era, but that's when it was widely adopted, right? And then because of this huge data explosion, be it because of like the internet, social networks, we have huge amounts of data, and the era of big data led to large databases, faster processing of more data, and good hardware that can deal with these huge models. So now we are like, it's still rising, as you can see, the curve is still rising. We have better quality models. We have very good processing ability. We are getting good results. So we see that all around us, right? So this is like a little bit about the history of AI in specific. And as you can see, this curve is just going up. And like the fundamental reason behind that is the ability to process too much data and extract meaningful results out of that data. So that's the reason we are here. And hopefully we'll not have another AI winter anytime soon. So that's good. Okay, so in general, we can say that deep learning is all around us. So we have seen, like, you go to social media, there are these deep learning algorithms that are helping you connect with your friends, tag photos, translate voice to text. And then there are so many other applications that are still in the pipeline, for example, autonomous vehicles. So most likely we'll have a self-driving car soon. Enough research has been done in that area. And also in many other businesses, like other businesses are also adopting this. For example, medicine, banking, those sectors are also kind of utilizing this power of deep learning to solve a lot of their problems. For example, credit card companies are using deep learning for fraud detection, credit card fraud. is a very like well-known application of deep learning. And then other businesses are also using this for like recommendations. And we talked about recommendations, and they are like almost on every web-based platform, right? So a recommendation is nothing but a deep learning model right now, because you have so much data and only a deep learning algorithm can capture that, right? So it's almost everywhere, and the range of applications is almost limitless. And when we go back and look at this curve that's like rising, this is giving us a lot of hope in AI as a field. And up to the extent that people have started to say that most likely AI is going to replace a lot of human activities and a lot of in areas where like we will need AI more than humans, right? So this is like a very optimistic sort of approach, because we have humongous amounts of data, we have the capability to work with that data, and we have some known algorithms that are really performing well on all these platforms. Right, so this is good as long as deep learning is used in automating processes, improving performance, detecting patterns. All of that is good, right? It's solving problems for us. But the question that arises, and the question that we are trying to answer in today's lecture, is that is this like overhyped, or is it something reasonable? And do we really think that AI can replace like all human activities as such, and can AI achieve human level intelligence? That's important, right? So maybe like in I would say in applications like detecting credit card fraud, or maybe like translating your voice to text, these kind of applications, if you look at the cost of AI going wrong, is low. Like even on recommendations, let's say it's recommended a person to you like on Facebook, but then you didn't know that person. So the cost of that wrong recommendation is not that huge. I mean, it doesn't hurt to see like one more person on that like recommendations list, right? But then there are like these applications, for example, the self-driving car. And there have been some known instances where a self-driving car has failed and caused like some damage, and like it has been into accidents where there was a loss of human life. And so that is something that's really disturbing, because we really want to make sure that if we are utilizing these algorithms, we are utilizing these models, we have to be like very sure, we have to be certain, I would say, that this particular algorithm is going to deliver what it needs to deliver without harming or making like, without having any such cost of human life involved, or any such thing that is like irreversible, right? So we don't want that kind of an uncertainty in our models. So that's the whole point of like trying to understand why there is uncertainty in neural networks, and what are the different things that we can do in order to deal with it, because it's important in many applications, right? And so there are like, if you just like go ahead and Google some of the known failures of AI, you can see accidents of self-driving cars, the Apple problem that we looked at, other biases that exist in these machine learning algorithms, machine learning algorithms classifying objects in a biased way, facial recognition, those kind of things, right? So if these algorithms go wrong in those kind of applications, or in medicine, for example, then there's a huge cost involved. And so we really care about the uncertainty. Okay. So I think like when we started talking about neural networks sometime earlier in the semester, I talked a little bit about the universal approximation theorem, which is kind of the heart or the core of neural networks. Okay. So because we are like so much excited about the like future of AI, and we really want to know whether like this deep learning is overhyped or not. So let's look at this fundamental theorem that talks about the power of any neural network. And so the universal approximation theorem says that neural networks can approximate any function. So that kind of gives us like, and there is this whole, you can go to the source and see there's a whole mathematical proof of how it shows that you can approximate almost any function. And believe it or not, they're talking about a single hidden layer neural network. It's not talking about deep networks. So basically it's saying that even a single layer network can approximate any function, right? So the thing is that there are two like caveats, so to say. So the first thing is the word used is approximate. So what exactly is this approximate? Is there a range to this approximate, right? and how far apart can it go. For example, if you remember the car crash in California, the reason for that like autonomous vehicle crashing on the sideways was there was some construction going on that highway that particular day, and the images that were fed into in the training process did not have that, and so it couldn't figure out like what to do. It couldn't make that decision, right? So yeah, it's approximating what like the road would look like and what it needs to do, what decisions it'll make based on that. But then there are things that it hasn't seen, right? So it will just approximate, and that approximation might cost us something, right? So this means like the function that it's computing is not exact, obviously, right? And the approximation can be improved by feeding in more data, showing it more pictures, right? Giving it more inputs. We can improve it, but still this approximate stays there, right? So that's one thing. And the other thing is the way these neural networks are designed, or the way they are created, is that we are usually computing continuous functions. Of course, like we are doing categorical outputs as well. For example, we were using probability estimates, right? And based on the probability, I was classifying things. But the way these were derived, the way they are built, is to capture continuous functions mostly. So in many discrete functions, we make another approximation of like going from continuous to categorical. And so there we lose some information, right? So as I said, like the generality does not hold for discontinuous functions, for example, right? And sometimes continuous functions like do not prove to be good enough substitutes for like these discontinuous functions. Sometimes they may not, depends on the application, right? Okay. So we have like discussed some limitations of deep learning models. Like we talked about transfer learning, and we said that there are biases. We cannot interpret these models. But today I'm trying to focus on some more, I would say, optimistic goals of AI, and trying to focus on the model itself rather than the data part, right? So we said that the bias occurs because this is the data that was fed into the model, and the model learned that there was some class that was overrepresented, and so that's why it's the output that it's giving is like the overrepresented class, right? That's what we said in like transfer learning type models. But today I'm talking more from the model's architecture and the way the model is designed itself. And so the first thing that comes into light is these adversarial examples. So what exactly is adversarial examples? The way a neural network is designed, or any deep learning model is designed, is that if you put garbage in, you're going to get garbage out, right? So it is a lot data dependent, right? And there have been some experiments, and you can go and read like one of the papers in the references. It talks about ImageNet. So if you remember, this is like a known images database, right? And if we start training on ImageNet, and we are trying to get like, we are feeding in, for example, this example was taken from that paper only. So if you're taking a picture of a, okay, so let me go back to the gradient descent part. So usually we are trying to minimize the loss and come as close as possible to the minimum loss, right? If I go in and perturb one of the image such that instead of like doing a gradient descent by subtracting that gradient value, I add the gradient of some other image into this one when I'm trying to classify whether this image is a panda or not. So for example, what I'm doing here is I'm taking a picture of a panda and adding it to like a monkey's gradient. And then I created some kind of like a doctored image, so to say, and I feed it into my like neural network, right? So the point I'm trying to make here is that we can get a neural network to classify this panda's picture as like a monkey, right? So we can like give it some adversarial examples, some examples that weren't like that weren't meant for that output. But like if we give it some different examples, we are going to get some very different results that we weren't expecting, right? So basically what like these networks are doing, they're mapping some input to some output. And so they're really dependent on what input you're giving them. And so the quality of these networks are as good as like the input data. And if you start giving more adversarial examples, the task that like it's trying to accomplish most likely will get, in some ways, it will start giving us different outputs, right? Which are like not as good. So that's the case of adversarial examples, right? The other important thing, which is like more, I would say, towards the fact that like AI is so much hyped and they're saying that we can get human level performance with AI, right? Now, there is a difference between how these models generalize versus how humans make decisions when they generalize. So let's look at like what these models do when we talk about generalization. You have you have created your own models, you've trained them on data sets, and then you've looked at their performance on test sets, right, on all your projects. So you've seen that if you feed some data to your network, right, the network learns those parameters, and then you can use those parameters to do some estimation on a new data set, which most likely came from the same distribution. That's what you're doing, right? So like if we look at this kind of a task, right, where we are trying to use either supervised learning or reinforcement learning to make, with this example, the problem of learning the appropriate launch parameters to get a rocket to land on the moon. Right, so let's say I want a neural network to like everything, to launch the rocket and make it land safely on the moon. Okay, so if we want to do if you want a neural network to do this, we need to train it with like some thousands or even millions of launch trials, right? If let's say this is a supervised learning, even if it's a reinforcement learning, we'll have to do actual launch trials so that like a lot of them, maybe 1,000 or like some millions are missed or are failed, right? And then the reinforcement learning algorithm will learn that this is the right way to do this, right? So why is this important? This is important because we are saying AI can achieve human level intelligence. Now, humans don't need to like physically launch these rockets to the moon before assessing like what can happen. Meaning we can make decisions as humans by visualizing these hypothetical scenarios and adding a layer of abstraction to the decision process. So for example, let's say you're crossing a road, right? You have like this picture in mind that like when a particular car or a particular vehicle that's coming is at a particular distance, then you can just like go ahead and cross the road. So basically you have this abstract model in mind, which hasn't really happened, right? Like you can think of all those scenarios, like while driving, you can think of all the scenarios right then and there. But in case of this AI model, whether it's supervised learning or whether it's reinforcement learning, the model has to go and see that, right? So if I train a neural network and say that this neural network is like controlling a human body and make this human body like navigate through like in a city without getting hit by a car. So the neural network will have to get that human body killed at least like thousands or millions of times, and to the point like when they learn that this is not what they were supposed to do. So those kind of things, like that level of abstraction. So the way humans think and like create abstractions of these situations of hypothetical scenarios and can like come up with like really certain results about those scenarios is known as extreme generalization, right? And that extreme generalization is not what a neural network can do. Your model can generalize as well as your data, as your training data was. Does that like make sense to everyone? Okay, any questions so far before we move on? Okay, so if we need like our models to have that like human level intelligence in decision making, in particular in systems that are like that have a huge cost of failure, then we need extreme generalization and not just local generalization. That's what we require. Then only our models are good. Otherwise, they're not. Right? So many empirical studies, they suggest that machine learning models. So this is another small thing that I wanted to mention. Although it doesn't really come under any of these, maybe it can come under adversarial examples. Sometimes you've seen, and this happens a lot in self-driving car experiments, that it's fed with certain images with particular backgrounds, and it tends to learn those backgrounds as well when we just wanted it to learn the image that's the focus, right? Or the object that was the focus of that image. Or sometimes you want it to learn the background, but it learns the object that's there. So those kind of things confuse the neural network, right? Those are enough to confuse the neural network. So like in a sense, we can say that a real neural network which has been successful until now, has the ability to map some input X to some output Y by doing some kind of a transformation. That's what we are doing. But and this has been very useful for many industries. In fact, this is what has been applied to like all web-based platforms or other businesses. But this is not something that we can just like carry forward and apply to every application out there, because there are costs involved, and we cannot just like ignore those, right? So that's why we need something that's known as models that account for uncertainty, right? So uncertainty in deep learning models, meaning, as I said, like usually in a deep learning model, we are predicting like some value, right? Either a probability value or like some point estimate, right? So we really need to know how confident we are in getting that estimate. So let me quickly show you an example. Actually, I remember this one, and you might see it in a lot of textbooks as well. So for example, okay, let's say we trained a network that is supposed to either predict whether this picture is of a cat or it's a picture of a dog. And then we feed it into a neural network. And this neural network is only supposed to output like the probability of like this being a cat, given this data, right? Or the probability of a dog, given this data, whatever the input data is. And because it's outputting probabilities, you know that the sum of these probabilities need to be 1. Right? So if like, so let's say I train my network and now I input like a picture of a cat. So obviously it'll maybe based on the features of the cat, the way it learned those features, it's going to get some probability for cat, right? So the higher probability, let's say 0.8 and 0.2 for dog, right? Now there are two scenarios in which our model, regardless of like whatever test scenario I'm giving it, it's going to give me some value. For example, let's say my test picture is like of a cat and a dog together in the same picture, right? And this example you'll find in a lot of papers as well. Now my neural network is designed to output these two probabilities of a cat and a dog. So it's still going to output something based on the features it learned, right? Let's say it said 0.5 and 0.5. Now it's up to me how I interpret these probabilities, and like with what level of confidence is it saying that this is like half cat, half dog? That's like the thing that I'm like really worried about. And in addition, let's say I input not a cat dog, but a horse picture, right? I'm still going to get some output for the probability of this being a cat or probability of this being a dog. And because the sum of these probabilities need to be 1, most likely based on the features of the horse, whether they match more with the cat or the dog, it's going to give a higher probability for that, for a horse picture, right? So those kind of things point to the fact that there is, of course, I'm getting a point estimate of the probability of whether this picture is of a cat or a dog, but I need some validation on how confident I am that this is a picture of a cat or a dog. So for example, in this case, it could have like given the probability of dog being 0.8, but with a very low confidence, right? Then I could say that this result means something to me. Otherwise, it's like literally telling me that this is a dog. Okay, so this like kind of example illustrates what like why we need like to capture some level of confidence, right? So when we talk about confidence, obviously, and when we talk about uncertainty, probability comes in, right? So or like in some other ways, you can think about the distribution of these values comes in, right? So what is the variance? What is the mean? And that in itself is going to give me some idea of like what is the confidence with which I can tell that this is like this lies in this range. So then I can say, okay, with this much confidence, I can say this particular probability would lie in this range. So that's what we are trying to do. And okay, let me see. Yeah, I think I talked about this one. Yeah. So one example that we just saw of a cat and a dog. Other examples could be like other edge cases. For example, of course, it's a picture of a cat or a dog, but then there is some like background with which my model is getting confused. And so it's giving me some like weird results. And so all those things need to be captured. And this is like a very like well-known saying by George Box, who's a well-known scientist in machine learning and AI. But all models are wrong, but some are useful. So all statistical models are actually wrong. But some are useful in the sense that I can establish some level of certainty in them that, yes, with this level of certainty, I can say that this could be this estimate, right? So we are just doing estimation. If you think about categorical output, or if you think about continuous output, we are just estimating some parameters of some model that is based on some data. So we are trying to estimate the parameters of that data from which these samples are derived, right? Because if you think about like, let's think about a regression problem in which you have like the continuous outputs. So if you think of all the outputs that your model is giving, the values will have a mean and a variance. So essentially, all I was doing was estimating the model parameters, estimating the underlying distributions parameters, right? So whether like it's a categorical data set or whether it's a continuous data set, that's exactly what I'm trying to do. And so there are some known types of uncertainties that exist in our like deep learning models. And they've been like actually divided into two categories, like two broad categories. So the first one is the epistemic uncertainty. And the second one is the aleatoric uncertainty. Now, the uncertainty that we just talked about, the uncertainty of the distribution itself, of the data distribution, is the aleatoric uncertainty. So think about the way you've collected the data, the way you're getting the data, or you're sampling from the given data, all of that, or if there is some measurement error. Let's say that like you have some sensor data and you need to do some prediction based on that, and the sensor itself wasn't working right. So there was this measurement error, and this is not your model error. But the thing is, you cannot do anything about it unless like somebody goes and changes the sensor itself and then collects a new data set. As long as you're working with that data set, you cannot do anything about it, right? So this aleatoric, the second one, it stems from data and it's like some kind of an irreducible noise. And there isn't much that we can do with it. So we have to live with it in some ways, right? And this, in some ways, we can say that it describes confidence in the input data. If there is already so much noise, then this is the best we could have done with this like data set, right? So let's assume that like we cannot do obviously anything about it. We cannot go and change the sensors from which we collected the data. So let's think about this epistemic uncertainty. We haven't thought about this before because until now, whenever we were talking about uncertainties, we were talking about the data distribution and the parameters that define that data distribution from which my sample was derived, right? But now I'm talking about model-based uncertainty, meaning there is some uncertainty that comes into my prediction because of the intricacies of my model, because of the way the like whoever designed this model or like whoever created this model and the way we are capturing the information and updating the information in my model, right? So that's known as epistemic uncertainty. And let's say if we add more data to my model, we can deal a little bit with it because then you're showing new examples to your like model. And so it has seen these like new examples and then it can learn more. So it has like seen more instances of the problem and then like maybe generalize well. So the uncertainty will go down, right? So we can reduce it to a certain extent by adding more data, but there are more, I would say, there are better methods of dealing with it. And let me show you the first one that's known as the Bayesian neural networks. So what exactly are these Bayesian neural networks? Let's try to understand that. Now, until now, the neural networks that we've worked with or we've seen are deterministic neural networks. Okay, why were they deterministic? So if you remember, like this is my input, let's say, and these are my hidden nodes, and let's assume I have some like two outputs. This one, right? So this is like a fully connected network. And what we were working with was like the weights, right? So we have like these different weights that we obviously update through a process and get some like final estimate of these weights, right? And so all of these have some like weights. on them. Now, if you think about these inputs like x1 and x2, for example, I do not change anything in x1 and x2. I just keep inputting the same data, the same observation again and again, right, in a deterministic neural network. So the output that I'm going to get from this neural network is not going to change much, because it's like exactly the same input that I'm giving. There isn't like beyond some point when it has like stabilized, there isn't anything to update. There is no new information I'm giving it. So most likely my weights will not change, right? So what happens in like a Bayesian neural network, that instead of having these weights as like these deterministic values, right? What we can do is we can come up with some kind of a distribution for these weights. Obviously makes it more complex, but the whole point is that instead of making point estimates of these weights, we are trying to capture the intricacy of the model itself and the way like the backpropagation, gradient descent, everything works. And we want to get like a sample of those weights and maybe estimate a distribution for every weight. So that's the fundamental idea behind Bayesian networks or Bayesian neural networks, that you place a probability like distribution over every weight. And so you know the range of values that that weight can take. And then every time like you feed forward, you have like the way we do that is like this Bayesian neural networks, they learn a posterior distribution over like these weights. Okay, so let me just like quickly write down what this does. So what we had, you must have seen this equation so many times before, but basically we are trying to find some probability for weights given my data and the output that I'm, because obviously like when it goes back, it is going to sample from the same distribution and then get a new point maybe, right? So we don't, because we are going to sample from that distribution when we do the weight update. So I don't know which point is going to be picked up. And so there will be a difference there, right? So basically what we have is something like this. So X. And then there are some like, but I'll show you what exactly we're trying to accomplish here. Okay, so this is like the famous Bayesian equation where we are trying to estimate this here. And this can be done. So now, obviously, like you know how complex a neural network in itself is. And now we are saying that we don't want to like make a point estimate when we do backpropagation, but rather like this distribution of values. So essentially, I'm trying to like estimate this thing in every like forward and backward pass. So this is in itself is like analytically intractable for like bigger networks. This is intractable. It can be done only for some toy examples, and that's about it. So how do we train these? Well, we don't need the exact value of this, but rather we can approximate something. So there are different ways of like approximating this. Like there are two very well-known ones. The first one is the dropout. So you must have like, we discussed this sometime earlier. Dropout was that we are dropping some of these neurons and then just like making the weight updates only for one neuron. So maybe like sample from some Bernoulli random variable, decide like which nodes to turn on or which nodes to drop, right? So based on that, we can reduce the amount of processing that will happen. And you can update like some of these weights in like one pass and some of the other weights in the other pass and so on, right? So that's like one technique. The second one is to use some kind of an ensemble learning in which you have like multiple like different models that are working with different inputs, and then they will get different weights, and then you can come up with the estimate like by using all those weights for like, for example, for W1, you will have some weights, right? And then for W2, you have some other weights. So you can come up with a probability distribution every time. Of course, just by looking at the, and just by like, I didn't give you the details here, but in this ensemble learning, when we have like multiple models, what we are doing is we are finding some kind of an expectation for my output given my input. And I'm also trying to find some variance for my output given some input. And this is what I need to get when I'm talking about uncertainty. So in some ways, I'm addressing that issue that I know that this is going to be the variance. And if the variance is huge, then I can say that there is like a lot of epistemic uncertainty in the model. And so we need to do something, right? if the variance is low, we can say that this is a high confidence model, so we can use it. That kind of, that's what we are doing. So yeah. Now, just by like looking at the explanation of like, or the definition of these models, you must be thinking that these are like really complex. And that's true. They are very time consuming. They don't scale as well, and they're very slow. Because if you think about the dropout, just for like one weight update, I'm doing like one single pass of dropout, and then I have to do so many to get this entire distribution for weights, right? So that's taking a lot of time. It doesn't scale well. It requires a lot of running time. And the more importantly, this probability distribution I'm talking about is dependent on two things. This posterior that I'm trying to estimate is dependent on, like, the most important thing, it's dependent on some prior distribution. So I do have some prior description of this distribution there, right? So I have to come up with that at least. And so that makes this overall process not as good when it comes to like practical usage of these models. But regardless, they give us some way of modeling this uncertainty in this neural networks. So just like high level, remember that instead of like getting point estimates of these weights, we are getting probability distributions. We are placing like some prior on these, and then we are like estimating. There are different techniques, obviously. We cannot just use the existing ones. But yeah, with these techniques, we are able to estimate these weight distribution. All right. Any questions so far before we move on? Okay, so that's fine. Let's see if, oh, I'm sorry, Lake, I didn't see your comment. Yeah, so your question is, it's easy to confuse image classifiers with text, like an orange with a paper sign that says Apple. And yeah, that's again an example of like an adversarial kind of an issue, an adversarial uncertainty, right? So yeah, as we are discussing, there is no like one way to fix this issue. Obviously, feeding in more data, looking at the actual results and seeing what we are getting. So, and of course, like this is more to do with the data itself. So yeah, we can confuse a neural network like that. That's correct. Okay. So the second thing is approximating uncertainty. Now, until now, we know that we are modeling some level of uncertainty because we are estimating the probability distribution of the underlying data in some ways. Now, when we talk about epistemic uncertainty, we are talking about the model uncertainty. So we can use sampling methods, except that we don't want to sample the data. Like, you know that we can get rid of like a lot of variation in like our results if we do multiple sampling, because then we can estimate some model parameters if we like keep sampling from some population, right? So we can apply some of that idea in order to get rid of this, or in order to minimize or reduce this epistemic uncertainty. Okay, what does that mean? How can we approximate a model uncertainty? One way is to sample it, and let me show you how this is done. For example, assuming I already have some aleatoric uncertainty, which I cannot help because it's there in the data. So I can do one thing, which is I have like some input X. This is how like we work with these models. And then you feed it into a neural network, which is like my first model, 1, right? And I get some output. So basically, I'm just like denoting it. So this is not just like one single run, but it is like multiple runs so that I can get some mean and standard deviation for this data set using this model. So let's say this is like a regression type problem, right? So I get some like, let's say this is mu1 and sigma 1 squared because this is model 1. Okay. Now what I can do is I can feed this same data into another model, model 2, and again get some like mu2 sigma 2 squared. And I can keep doing that like maybe n times until I get like this nth model, so mu n sigma n squared, right? And every time I'm doing this, right? This is giving me some kind of like data uncertainty, because these model parameters, in some ways, they represent the underlying data. And that's what I'm trying to learn, right? These parameters are like what represents my data. Now, if I go and plot these, let's say I have some kind of a plot wherein I have some mu and sigma squared. So the first one, let's say, lies somewhere here, right? So that's the first point, mu1, this one. And then this is the second one, third, fourth, fifth, and so on. So I can get like a whole distribution of these values, right? I can get entire distribution of the output of all these models. That's clear to everyone, right? So like in particular, like if we look at one of the estimates, like I wouldn't say one estimate, because these will also be a range of values, and that's how I'm getting the mu and the sigma squared. And then I'm using that to plot on this one, right? And so if I look at this here, and the variance of all these models taken together can be described by like how much this varies here, right? In some ways. And like, what is the spread here? So this is kind of giving me an idea of like the entire output of all these models in some ways, right? So if this is like really small, if this window is like pretty small, then I can say that like all the means lie within this range. And so, yeah, this is like a high confidence model in some sense, right? If this was like really spread out, then I cannot comment as much. But regardless, I can say one thing for sure is that when we were getting these model outputs and when we were getting these distributions, right, we were focusing more on the data side. But this new distribution is giving me some information of my model itself, right? So it was the same model, except that maybe I changed some weights initially, initialized it in a different way, and I got like some different values. I might or might not, but most likely I will get a different value, right? So this entire spread or this new distribution is giving me some idea of my model uncertainty or the epistemic uncertainty, right? So what we can do is, instead of sampling data, we can sample these models and we can try to come up with the approximation of the underlying techniques, right? So in some sense, what we're doing is, this is also a distribution in some sense. So how about I try to estimate the parameters of this distribution, right? So this is known as, this is like, there's a term for this, and this is known as evidential deep learning. That means I'm trying to treat learning as an evidence acquisition process. I had these neural network models that gathered some evidence about the models, and then I came up with this high level distribution. So this is another, like, this is a level ahead of these distributions. And now, can I estimate the model parameters of this model? So if I can estimate the model parameters of this model, which is a higher level model, then I can talk more about the uncertainty of the model itself rather than the uncertainty of data, right? So this is known as a higher level model. And in particular, this technique is known as evidential deep learning. So if you ever come across that term, that's what it is. I have a paper on this one, the one that like came up with this idea. So evidential deep learning actually deals with these higher level distributions. Also remember that this distribution in itself will have like different parameters, which might not be these, right? So it will have its own parameters, like, I don't know, some alpha or some gamma. It depends on what type of problem we are solving. So based on that, there are some known distributions for this high level distribution as well. For example, if you're doing a categorical kind of an output, then there is this Dirichlet prior distribution that people use to model this. Or then there are, like, you can use normal distribution as well, but then this becomes more complex than the ones that like were describing the data. But this is so the question arises, why is this useful, right? This is useful because we have more evidence, or maybe like we are providing more evidence to, in some ways, show how confident we are in using this model to get these results. So the more evidence we have, the better it is, right? And so let's say, like, I can, let me just get rid of this one. So for example, if like my output comes something like this, so this is my evidential distribution. So from now on, we can call it evidential distribution. So if it is like this evidential distribution is very narrow here, right? And it doesn't like spread out as much, right? So we can say there is low uncertainty in this model, right? So there's low epistemic uncertainty. I cannot comment on epistemic uncertainty by just running a single neural network, because that neural network and the uncertainty I'm getting is of the data and not of the model, right? And so if it's like really spread out, right, in all directions, then I'll say that like this, there is high uncertainty in this model and high epistemic uncertainty. So those kind of things, yes.
What if like all except one point is clumped up and then just 1 point is an outlier that's like really far from the
Yeah, that's an excellent question. So then there are the same statistical techniques that apply here. So if it's an outlier, either you just say that it was like a one-off case, or you run more experiments to get like more data here to like be like very confident that this is a high or a low epistemic uncertainty. So that's an excellent question. Like basically you mean if there was a point here, right? And so that could have been just that one instance when the model didn't perform well. Yeah, that's a very good question. So as I said, because this is also a distribution in itself, so the rest of the techniques stay the same, right? So we can use the same techniques. Just remember the model parameters will be different here. That's the only thing. Otherwise, the rest of the techniques for estimating the model parameters stay the same. And we can comment more on like how confident we are about using this model. And we can make some comments about like the data itself, right? And the model also. So then like we are adding some evidence to the fact that this, like we are confident in using this model. That's why this is known as evidential deep learning. It's a new research area. I'm not going into the details of how this is done, how the estimates are done, because it's a more complex process. But I have this paper here, which you, if you're interested, you can go here and read this, like how to do classification and how to reduce classification uncertainty using evidential deep learning. So of course, like if you just read the abstract, it says, this is different from the Bayesian neural networks that indirectly infer prediction uncertainty through weights uncertainties. So remember we said that like when we are doing the Bayesian networks, we're saying the weights have uncertainties. But here they're saying the model themselves have uncertainties. So let's like capture that. And let's try to understand the distribution of those and come up with a new distribution. So as far as I remember, they do some, I think, digit classification problem. That's worth reading. Okay, don't think it's the same paper, but yeah, reading this, this one is also a good paper. In fact, like this is one of the early papers that came in and talked about evidential deep learning. So this is the one that whose source I've provided here with evidential deep learning. And there are 3 more readings or 3 more papers that I would highly recommend reading, because they have like a very good, for example, this one has a very good practical side to it, like the practical perspective. Remember when we said like there is this local generalization versus actual generalization when we are comparing AI with human level performance. So this paper really talks about that in like detail of how we cannot compare AI and its generalization with human level like generalization, like how humans generalize. So like real generalization would be when these AI machines can think like humans, right? So this is the first one that talks about that. Yeah, this one. Yes, this is about the adversarial settings and how like a deep neural network can be fooled. What are some of the things that we can do? What are some of the strategies that can be applied? So I think this was one of the 2016, no, this is not the Google one, but yeah, what happens if we explicitly add distortions to the training data? What happens when we add distortions to the test data only? So those kind of things, like how can we deal with that? So this is also a very good paper. I tried to put only like those readings that I feel are like really can be useful for like if you're really working on something that requires like some level of confidence and you need to somehow capture uncertainty in neural networks, it's definitely worth a read, this one. Okay, and then the last one. Yeah, so this is another thing, like I didn't mention it explicitly in the lecture, but I thought I can just like put this paper there. We can also deal with uncertainty by changing the structure of the networks. And that cannot be done in every type of network, so it cannot be generalized, but this can be done in like graph-based approaches. So usually the uncertainty in graph-based approaches is easier to capture and easier to like interpret. And so convolution neural networks, when used as like graph-based networks, can handle this particular like aspect of deep neural networks really well. So this paper actually talks about like how can we like this talks about everything about a graph neural network. So in the structure of the neural network itself, we can capture this uncertainty in graph-based models. All right, so I think that's all I have for today's lecture. And we have like one more lecture left where I'll talk more about new frontiers in AI and deep learning and new research areas in deep learning, but that's it. Like we have 25 lectures in all. And yeah, feel free to ask questions on the discussion forum about if you have any about the project presentations. Add your like team and your preference for your presentation on the Excel. And yeah, and if you have any other questions, just like feel free to ask on the discussion forum.